data poor, but hopefully idea rich, and I'm going to try and be a little bit stimulating and perhaps even a little bit controversial. So this talk is co-authored with Ingrid, who's visiting from the Netherlands. I presume the red thing at the top means turn off the machine. Good. So this talk is based on a draft manuscript that we've prepared. It's about the concept of living on borrowed time, which I'll explain in a moment, about transgressing or crossing unrecognized tipping points or thresholds that separate alternative stable states. Now, the jargon load in this research arena is pretty horrendous. So alternate stable states, regime shifts, tipping points, it's a bit of a mess, so I'll try not to get bogged down in too much of that. And those are the co-authors, which include some people who are mathematically talented. So I'll show you some predictions from a model. I'll forgo the shock and horror treatment that Sally used last night with an equation. I'll just go straight to the model result. So this is a familiar picture. We've seen it in several of the talks. This is the typical phase shift or regime shift from a coral-dominated system over here to a macroalgal dominated system over there. And one of the points I want to make today is that these kinds of regime shifts often unfold very slowly, which makes them hard to detect and makes them easy to ignore. Now, you may be surprised to hear me say that they unfold slowly, because probably the best studied regime shifts in the ecological literature are for shallow temperate lakes, mostly in Europe, which typically undergo a regime shift from a clear water to a turbid water system over a period of months. But for other systems, and I'll give you lots of examples, that kind of bistable dynamic, to use another set of jargon, can often unfold very, very slowly. The thing that makes either of these two alternative states stable is two sets of feedbacks that maintain the resilience of either the coral-dominated state or the macroalgal-dominated state. So if we consider the typical healthy reef, it's got high coral cover, and as Luke Smith's talk yesterday demonstrated, high coral cover means a high level of production of juveniles, which tends to mean high levels of settlement. As Morgan's talk just a moment ago emphasized, high coral cover also equates to high structural complexity, three-dimensionality, which is good for fish. Some of those fish are herbivores. Herbivory maintains bare space, and that's good for coral recruitment. So all of those processes provide positive feedbacks that maintain the resilience of this system so that it can last potentially a very long time. But equally, there are positive feedbacks in this system that make it resilient. So high cover by macroalgae means this is a terrible place to be a baby coral. They can't penetrate that thick mat of seaweed, and if they do manage to settle successfully, their chances of growing up and reproducing are very slim because of smothering, shading, whiplash, and other terrible things that macroalgae do to juvenile corals. So it too has positive feedbacks that means that it is also a resilient and potentially very persistent system. Now, this audience is probably most familiar with ecological regime shifts like this, but there are other regime shifts in different systems. We can think of the Wall Street crash as an economic phase shift, the French Revolution as a social regime shift, off with their head and all of that. We can think of bistable dynamics in climate systems. If you're mathematically talented, unlike me, you can write an equation that describes this transition and the feedbacks that maintain these two alternative states. That same equation could describe an ecosystem, a social-ecological system, or a linked climate ecological system. So consider, for instance, what's been happening to Arctic ice over the last 50 years or so. The ice is shrinking. And the dynamics of what's been happening to Arctic ice in the summer has been described by a mathematical model, very similar to one that I'll show you in a moment for coral reef ecosystems. The ice is shrinking, and as it shrinks, the whiteness of the ice is diminishing. So its albedo is diminishing. I wrote that word down so it didn't say libido by accident. Icebergs don't have libido. But as the ice shrinks and as the ocean water warms and the currents change, there's a positive feedback because more black water heats up faster. And so we seem to already be living on borrowed time in terms of how much longer we're going to see Arctic ice, and it's predicted to disappear in the summertime over the next 30 to 50 years. So I would argue that we've already passed a tipping point for summer Arctic ice, when atmospheric carbon dioxide reached something like 350 or perhaps 300 parts per million. So that's the concept I want to try and develop today. If you look at the ecological literature in relation to regime shifts, you see terminology like catastrophic shift, sudden flips, ecological surprise. So the inference from that sort of language is that regime shifts are necessarily very sudden events. But even for ecological systems that show quite rapid regime shifts, the lead up to reaching the tipping point can often be very protracted. So even for lakes, it can take a century or longer for the amount of phosphorus in the sediment of a lake to accumulate to the point where it passes a tipping point or a threshold, due to, say, land clearing in the catchment of the lake or increased urbanization over a period of many decades. So even rapidly shifting regime shifts are preceded by a long period of build-up prior to transgressing a threshold. One example that is very familiar to most people, but which is not typically thought of as a regime shift, is the interaction between climate change at the end of the last ice age and terrestrial vegetation. Climate scientists now have changed their thinking about the speed of temperature rise at the end of the last ice age. So the new thinking is that there are very rapid increases in temperature in places like Greenland and Iceland over a period of a few decades rather than millennia. But the response of various parts of the climate and ecosystems to that fairly rapid temperature increase at the end of the last ice age was much, much slower. So we know, for example, that sea level rise took about 8,000 years to equilibrate after the end of the last ice age to its current levels. If we look at the terrestrial plant literature for the last 14,000 years or so, at the end of the last ice age, plants began to move from a warm refuge in places like Florida or the Mediterranean in Europe northwards. And they moved at very different speeds depending on species and species-specific capacities for geographic range expansion. So for a period of many thousands of years, we had non-equilibrial or transient terrestrial plant communities as different species, beeches and willows and chestnuts and so on, expanded at very different rates at a continental scale, moving polewards many thousands of years after the climate had already shifted. So that's the concept I want to talk about today, transient dynamics during regime shifts from one stable state to an alternate stable state. So a little bit of theory. Again, this is probably a familiar diagram to many of you at this stage. This is ecosystem state on the y-axis, so we can think of a coral-dominated state as one alternative, and a coral depauperate state dominated by seaweed or sponges or something else that is arguably less desirable. These are the slow drivers in the system that change the system from a pristine condition to a highly human impacted system. I've put all of these drivers on the x-axis because they all act simultaneously and they're highly interactive. Even though if you look at the literature, and indeed if you listen to some of our talks, you would think that these were very separate issues, but of course they're not. So healthy coral reefs can absorb a certain amount of these, what some people call stressors. I prefer to call them drivers of change, until they eventually reach a threshold and then they tip into an alternative state. And both of these, as I mentioned, can be highly resilient because of those positive feedbacks. So the yellow line here shows the equilibrial ecosystem state that we could anticipate observing for a given level of these slow drivers. The other part of that dynamic, though, is much faster, and that's indicated by these white lines, and these are sometimes called fast drivers of change in contrast to these slow ones. And this is things like cyclones, crown of thorns outbreaks, bleaching events, ship groundings, and so on, that disturb the ecosystem away from its equilibrium state down in this direction, and then they recover. So yesterday we heard a couple of examples of this sort of disturbance away from an equilibrium and recover back to it. In the plant literature, that's called succession. So we heard Luke Smith describe the aftermath of a bleaching event on Scott Reef and the slow recovery afterwards. We heard Dave Williamson talk about disturbance to the Keppel Islands and the recovery through regrowth of coral fragments back to the coral-dominated state. Neither of those two examples were a regime shift from a coral-dominated state to an alternative stable state. They were simply disturbances and recovery afterwards. Now, everyone in this room will likely accept the fact that that sort of disturbance recovery cycle takes time. So typically the recovery or succession after a crown of thorns outbreaks might take a decade or two. But equally, probably most people in this room think of transgressing this threshold as falling off a cliff, where you suddenly undergo a flip, an ecological surprise to the alternative stable state. And that's simply not the case. And I'll show you some data which says that this transition from the coral-dominated state to the alternative can also be very slow. And there are two components to that. There's the build-up to reaching the threshold, which can take centuries. And there's the succession-like unfolding as we make this transition from coral dominance to macroalgal dominance. One other point while I've got this slide, the usual metric of coral reef resilience and coral reef health, which is a term I hate, is coral cover. And it's not a very useful metric of coral resilience because coral cover can be high up here in the coral-dominated state or it can be low down here in the coral-dominated state if you've just had a disturbance that you're going to recover from. Equally, coral cover can be very high here in the macroalgal state at the early stages after you've transgressed the threshold but before you begin the inexorable decline. These are sometimes called alternative basins of attraction, which is another set of jargon. So in this basin of attraction, if you're disturbed, you're attracted back to this equilibrium. In that basin of attraction, if you're disturbed away from this equilibrium, you're attracted back to it. You'll notice that there are two thresholds in this. So that displacement of a forward downward trajectory and a backward upward trajectory is referred to as hysteresis. And hysteresis arises because of the reinforcing positive feedbacks that maintain this state or that maintain that state. Okay, that's some theory. Most of the studies that you read in journals about regime shifts tend to focus not on these slow drivers and on the 200 years it took to go from being pristine to being degraded enough that you enter a new basin of attraction. Rather, they tend to focus on these short drivers, which if they're strong enough, can tip you over that dotted line into a new basin of attraction. So if you read the coral reef regime shift literature, it tends to emphasize the straws that break the camel's back. The latest bleaching event, the latest crown of thorns outbreak, the latest cyclone that people have experienced through the prism of a 3-year window that is their personal scale of studying a regime shift. And the point I want to make is that regime shifts take a long time, both in the lead up and in the slow unfolding once that tipping point has been transgressed. Okay, so this is one type of response that ecosystems have to slowly building drivers of change, but it's not the only one. This is called a hysteretic response, because this threshold and that threshold are displaced along the x-axis. So that's the one here I've just shown you, but there are two others. This is a threshold response without hysteresis, which is more readily reversible, shown here by these arrows, than this one. In fact, there is a fourth type of transition which Brian Walker has called my attention to. If that backward threshold actually hits the y-axis, then you have hysteresis which is so strong that the regime shift is irreversible. So if your forest becomes a desert or your grassland becomes a salt pan, then effectively, hysteresis has gone back to the y-axis and it becomes irreversible. Now, I should have started to explain this slide by explaining what the axes are. So the y-axis here is equilibrium ecosystem state, and this is the slow drivers of change that I described before. There is no time component to this graph, and that's equilibrium. So if there's a small increase in this environmental driver, then the state of the ecosystem will move from here to, say, here, got a shaky hand, and eventually equilibrate along that line. But remember, we've also got our short-term fast drivers which displace us away from that equilibrium curve. But if you read the literature, and these graphs appear in many different contexts in the regime shift literature, people invariably lose the word equilibrium on this axis, and they often switch this axis labels for time, or they confound it with time. So often this gradual, this smooth transition is often described as a gradual transition or a slow transition. So people are swapping a temporal connotation when there is in fact no time on this graph. They'll often describe threshold and hysteretic responses as sudden responses or catastrophic responses. So they're actually confusing a timeline with the equilibrial response, which can actually take decades or even centuries to unfold, as it did, for example, with the expansion of plant communities at the end of the last ice age. So what I'd like to do next is model temporal changes in ecosystems responding in these three different type of ways. So I'm not going to spare you the equations, but the next graph will show how an ecosystem responds through time if it's behaving smoothly with a threshold or with a hysteretic response. And I'm going to do it for two types of ecosystems: an ecosystem in white that responds quickly, or a model ecosystem where we've introduced a lag term, so the ecosystem responds much more slowly. So if we have a smooth response at equilibrium, both a fast responding ecosystem and a slow responding ecosystem will have this smooth trajectory. But look at the slow responding system. If it's behaving with threshold behavior or hysteretic behavior, it's almost exactly the same as if it's responding smoothly to a gradual change. In other words, if you have an ecosystem that responds slowly to transgressing a threshold into an alternative stable state, you don't know whether it's actually past a threshold or not, because the response is incremental, it's slow, and it's smooth, even though it is behaving with threshold dynamics and with hysteresis. The fast one, you can tell the difference. But coral reefs are not fast ecosystems like lakes. So we are looking in many parts of the world at slow incremental loss of coral cover. And I would argue that in many of those cases, we may actually be looking at the unwinding of an ecosystem as it has already entered a new basin of attraction, that it's inexorably approaching a new equilibrium at a low coral cover, which will be very hard to reverse if hysteresis is operating. Okay, so I'm waiting for time. Bad. Okay. In 2009, I wrote a paper with Johan Rockström and 28 of our closest friends, which was published in Nature, and it introduced the concept of planetary boundaries. And we identified 9 Earth systems which we thought we could identify thresholds, not necessarily thresholds that are hysteretic, that would be very wise for mankind to avoid. So these are the 9 systems we looked at, and we stuck our head out and actually put numbers on these. So for climate change, we thought that transgressing a tipping point of 350 parts per million would be a really bad idea. The response by the reviewers to this manuscript was pretty interesting. There were 4 of them. They all thought it was really interesting. They all thought, they didn't believe a word of it, but it should definitely be published. And so it was. So it's very likely the case for many of these putative thresholds that we have in fact already crossed them. And that raises the issue of living on borrowed time. How long can we stay on the far side of a threshold before the new regime, which is likely to be a bad regime, will eventually lock in as the positive feedbacks become stronger and stronger and make reversible transitions to the correct side of the threshold no longer possible. So that's basically the concept. So this is basically 3 propositions that I want to explore today. The first proposition is that many ecosystems, including I think many coral reefs, are already living on borrowed time because we haven't recognized slowly unfolding regime shifts that are already well underway, that we've already passed these thresholds into new basins of attraction. And another point I'd like to make is that failure to recognize the fact that we've crossed tipping points generates a shifting baseline, and it skewers our capacity to detect these regime shifts. And finally, delayed responses by ecosystems after they've crossed the threshold could in fact afford an opportunity to return to safer conditions before that regime shift eventually equilibrates. So living on borrowed time might have a positive side if we can recognize the fact that we're living on borrowed time, that we have in fact already crossed the threshold but haven't yet locked into the new regime. Then potentially we can move backwards to the right side of the threshold. Okay, here's some old data of mine published in Science a long time ago, which shows the sort of classical regime shift from coral dominance to macroalgal dominance. And the point I want to make here basically is the time scale here is roughly 20 years. So this is arguably one of the most detailed studies of a regime shift. So this is coral cover through time over 20 years goes down, and this is macroalgal cover over a similar time scale, and it goes up. So it wasn't an overnight phenomenon. And if we look at larger scales like the Caribbean Basin, we can see similar sorts of regime shifts unfolding over multi-decadal periods. So the term ecological surprise, I think, is wrong because it infers it's sudden, and it tends to focus mostly on the straw that breaks the camel's back, the most recent disturbance, rather than the lead up to transgressing a threshold and the slow unfolding that occurs afterwards. So why are some ecosystems slower than others in these unfolding regime shifts? Well, one is that the gradual approach to a tipping point can take different periods of time, but it can be centuries or even millennia. So the transitory dynamics that I described for continental shifts in terrestrial plant assemblages after the end of the last ice age is, I think, a good example of a regime shift following the transgression of a tipping point in temperatures at the end of the last ice age. It lasted for thousands of years. There are a whole slew of biological processes that are very well studied, things like colonization, geographic range expansion, longevity of long-lived organisms, that are very rarely tied into regime shifts. But I think that's just a small number of processes that cause regime shifts to unfold very slowly. A key issue is that different species respond differently to changing conditions. So changes in slow drivers will elicit much more rapid responses in short-lived species compared to long-lived species. And so phenomena like time-delayed extinction, the storage effect, which the ecologists will be familiar with, and extinction death, those are all processes described in a huge ecological literature, but very rarely tied to this concept of slow regime shifts and borrowed time that I'm developing. Okay, so I want to move on now to this second proposition, which is that failure to recognize transient dynamics causes some issues with monitoring and how we interpret regime shifts. So I'm going to illustrate that with two papers in high-profile journals from the mainstream ecological literature. So the top one there was published in PNAS, and it's about a rapid transition, a regime shift in coral reef communities, and the impact of two particular disturbance events. This study was done relatively recently and for a relatively short period of time. So I want to put it in context of what's been happening over a longer period throughout the Caribbean. So this is a graph that shows Gardner et al.'s meta-analysis of coral cover in the Caribbean basin over the last 40 years or so. And these authors show a regional scale decline. This is the study that I described from PNAS, which is much shorter. They describe this as a rapid regime shift from a coral reef which was originally pristine with 15% or so coral cover and about 30% macroalgae at the beginning of their study. Coral cover went down to about 5%, macroalgae went up to about 50%. So they describe this as a rapid regime shift. It wasn't. I think a more parsimonious explanation of this trend is that it's part of a Caribbean-wide trend. And these guys came along very late in the piece, and they described the tail end of a much longer regime shift, which has been occurring for a long period of time, many decades, across the Caribbean basin. The other study that I'll mention briefly is by Bruno. Bruno did another meta-analysis where he collected data from about 3,500 sites where people had measured coral cover and macroalgal cover, and he plotted one against the other. So basically he was substituting space at 3,500 sites for time, and his expectation was this graph would show two clear clusters of points with a coral-dominated low macroalgal cluster at one end of the graph and a macroalgal-dominated low coral cover at the other end of the graph. He didn't find that. Instead, they found a mess of points which describes a triangle, and this was their interpretation. So surprisingly, few of the reefs fell into either of the classically defined clusters of points that I've just described, and a large majority were between those extremes, and the italics are mine, a pattern which is not concordant with the belief, this is not religion, that coral reef communities switch between coral and macroalgal dominated states. Now I've italicized that bit because it's not good logic, and I'll explain why with my own data from the Caribbean, which I think most people would accept is a proper regime shift. So there's the data I showed you a minute ago. And this graph, which I hope you can read, is a plot using the technique that Bruno used to identify regime shifts. So this is coral cover from all of these points, plotted against, coral cover plotted against macroalgal cover using these data. And it shows one cluster in the 1990s and another cluster mostly in the 1970s. But I've generated the same triangle of points that Bruno used when they substituted space for time. So basically, these are transient dynamics that obscure the endpoints. So you can't find endpoints if there are lots of transients. And in fact, Bruno demonstrates the importance of long-term transitions between these two final endpoints. Okay, I want to move now to the end of the talk and deal with this third proposition. And I'll do that using a model which looks at the impact of reversing slow drivers of change for systems that respond either quickly after they've transgressed a threshold or that respond more slowly after they've transgressed a threshold. So this is a model prediction. At the bottom, we've got a trajectory of a slow driver, which is changing the dynamics of the system. So this could be climate change or parts per million of CO2 through time. This is a threshold which causes a regime shift. This is an overshoot, business as usual. Finally, we realize there's a problem with this driver reaching excess levels and we reverse it down to a new low level. What happens to an ecosystem in response to that driver of change if it behaves quickly versus slowly? Well, for a fast behaving system, as soon as it reaches the threshold down here, it collapses, and it stays collapsed until the driver is reversed to a sufficiently low level below the hysteretic threshold, and so and at which point it quickly reverses back, say, to a coral-dominated state. For our slow system, it also collapses, but it collapses much more gradually, which would make, I think, it much easier to be less concerned and to ignore this gradual decline in ecosystem state. And once the driver has been reversed, it too will slip back up, but it will take much longer for it to revert back to a coral-dominated state because it's a slow-acting system. Now this is an example where the intervention, the reversing the driver took a long time to happen. What happens if we get our act together, if we have a really good monitoring program that says when we reach, say, this point, we need to revert the driver now rather than at some point later. So let's look at that scenario. So this is the same model, but in this case, the intervention is much more rapid. So here's the driver going up, it exceeds the threshold, but soon after that we realize there's a problem and reverse it. The fast system collapses quickly, as before, but because we've reversed the driver, it stays for a shorter period in the collapsed state, and then it reverts quickly. But the interesting point is what happens to the slow system under this scenario. It's slowly degrading, but because our monitoring system is so well integrated with our management and governance, when we get to about here, we say, there's a problem here, let's revert the driver quickly. If we do it fast enough, if we reverse the driver here, we actually avoid the regime shift. And what's, I think, counterintuitive here, and really interesting, is that the slow responding system begins to recover quicker than the fast responding system. The fast responding system is stuck because of positive feedbacks in the degraded state for a long period of time, while the slow responding system is actually on a trajectory to recover, even though the fast responding system remains locked into this degraded state. So what I'm referring to as borrowed time is this period here, where we've passed the threshold, we're on our way to a degraded state if we continue with business as usual, but we still have time to revert these drivers of change to get back to the original non-degraded state if we act quickly enough. The trick, I think, is to have good monitoring systems in place that are well connected to systems of governance to allow this to take place. And so let me finish with going back to Gardner et al.'s trajectory for the Caribbean. I would argue that this is actually a regime shift, which is slowly unwinding at the scale of the Caribbean. The lead up to this regime shift probably took about 200 years. The slow drivers were building human populations in the Caribbean basin, increased levels of overfishing, increased levels of nutrients, and only in the last 25 years or so, increased issues with climate change. So climate change is a new threat, if you like, that's superimposed on these other long-term drivers. I think we probably passed a threshold for the Caribbean sometime around the 1960s or 50s, and since then, since monitoring began, we've documented the slow and probably inexorable decline to a low coral cover state unless we reverse those slow drivers of change. And we are running out of time because this is a long period of borrowed time. Now, I haven't got a graph of the trajectory of coral cover on the Great Barrier Reef, but Hugh Sweetman published one this year which shows a 40% loss of coral cover on the inner Barrier Reef between 1984, I think it was, and 2004. A decline that's not altogether different from the broad-scale decline that's occurring in the Caribbean. So it may actually be the case that the inner Great Barrier Reef has also passed a threshold. We're not cognizant of it because it's a slow, incremental decline that we're documenting. It's not what we might expect of a regime shift, an ecological surprise with a collapse. It's a regime shift in slow motion. And I think that's entirely feasible as a dynamic which is occurring. So I think we are living on borrowed time when it comes to nearshore reefs on the Great Barrier Reef. Mid-shelf reefs have also declined in coral cover by about 1/3, according to Hugh Sweetman's Ames monitoring data. So I think business as usual in the face of these sorts of declines of coral cover on the Caribbean, on the Barrier Reef and elsewhere, is a real warning signal that business as usual will take us, I think, inevitably. It might take another 50 years to a new low coral alternate stable state that most of us in this room wouldn't like to see happen. We've got a couple of decades to turn it around. Thank you.
We're on borrowed time.